welcome back. In the last class, we have discussed about steady state and dynamic response of single area system. We have discussed about the single area system in our last class. We have also observed that the dynamic response of the system was for a free governor operation, assuming that the manual speed change setting is held constant. So this was the response of delta F with respect to time. This is what we have observed before it is finally settling down at some value. And this is called as the steady state. Normally, ideally, we want the change in frequency to be zero, isn't it? In order to get it back to zero, what I am supposed to do? This has happened due to change in demand, because the demand has changed, so was the frequency changed. So in order to counter this one, this can be countered with manual change of speed changer setting. So I can manually change this speed changer setting, delta PC. So I can counter this delta PD. So I can bring this one back to, I can bring it back to zero. This can be done by manually changing the speed changer setting. But most of the times we don't prefer any manual control in modern day systems. So we need to go for some other way where it can automatically bring its steady state value of delta F to zero. So now we will look at one particular way where we can get the steady state value of delta F to be zero without any manual control of speed changes setting. Okay. Now, this can be achieved. This can be achieved by feeding back the delta F signal through a controller. This can be achieved by feeding back the delta F signal through a controller. So first let us draw this complete block diagram of isolated power system. Next we will move on to what best we can do. Right. This is the complete block diagram of isolated power system, or what we call it as a single area system, isn't it? Now, this is your manual control. This is an automatic setting, right? because of changes in demand or your manual speed changes setting, there will be a change in frequency. Normally, the demand will be varying, so frequency will be varying. This will be countered by your manual change of path. But I may not need this manual speed change setting now. So what I'm doing is nothing but I'm going to remove this manual speed change setting. So how I'm going to do this one is I'm going to employ a feedback signal. This is my feedback signal, and I'm going to employ Ki by S. This is an integral controller. This is integral controller with a gain of Ki. Ki indicates the gain of the integral controller. Now this is being fed back in the place of manual control with negative feedback. With a negative feedback. So I'm removing this manual control. Instead of that, I'm going to employ integral controller back to the system with a negative feedback. Now let us see theoretically whether this can really reduce the steady state value to 0. Okay. So before going for that, see how many inputs are there to this system now. This is only one input, right? Delta PD, because I have removed the other manual input. Instead of that, I have provided this feedback, isn't it? So now let us simplify this system now. Before going for the simplification of this system, now, we make sure this is the only input, this is the output, this is the forward path of your function, and this all, they will act as a feedback to your system, because this is the main forward path. This entire thing is the feedback, isn't it? So now I'm going to redraw this figure now. See, these two are two feedbacks, isn't it? So these two are the two feedbacks. So I'm going to join these two because these are in parallel. So what I will do, I'll do it as 1 by R plus Ki by S. And this is to be fed with negative feedback, right? So that negative feedback, I'll write it. Understood now? So now this has become a PI controller now. Earlier there was a proportional controller, now integral controller. Now this is PI controller. Proportional plus integral controller. Okay. Now see here, this entire 3 will act as a feedback for this one, isn't it? So now I'm going to join all these 3. Yes. So this is your feedback, negative feedback. So this is also actually a negative input, right? So I'm just mentioning it as plus and here minus. So this is your input, minus PD of S. For our convenience, I'm doing this one. So this is G, this is H with a negative feedback. So what is the overall transfer function type? The overall transfer function of this one is delta F of S is equal to, so first of all, let me write delta F of S by delta PD of S. So what is the overall transfer function? G by 1 plus GH, isn't it? Where is G? This is G. By 1 plus GH. 1 plus KPS into 1 plus S2PS into, this is all the feedback, right? So KT by 1 plus S2T, KSG by 1 plus S2SG into 1 by R plus KI by S. Isn't it? So here it is minus PD of S, so I'm taking it as minus PD of S. So if I write it here, this is my overall transfer function of the system. Now, having said that, now considering delta PD is constant, it is not PD, delta PD is constant with respect to time. Okay. So what is delta PD of T? It is some constant K. Instead, I'm taking it as delta PD only. So what is delta PD of S, guys? If it is a constant, if it is A, so automatically A by S. So it is delta PD by S. This is the value of delta PD of S. Okay. Why? Because I have considered this one constant with respect to time. So I'm going to substitute this one here in this one. Also, steady state value of f of t or delta f of s. So how to determine the steady state value? Limit s tends to 0, h into f of s, isn't it? H into f of s. What is f of s? This value is delta PD of s. You will substitute it here. So now I'm going to erase the figure and I'm going to write this one down. Yeah. So steady state value is equal to limit s tends to 0, h into f of s, right? So what is s into f of s? This is s into f of s is, first of all, we are supposed to bring this one to here. So minus is already there, minus delta PD of s is delta PD by s into, this is the transfer function, right? Kps by 1 plus s into 2ps by 1 plus kps by 1 plus s 2ps into kt by 1 plus s 2t into, I'll take the LCM of this one. This is SR plus S plus RK. Okay. So this is my transfer function. So I'm gonna take an LCM of this one. This is S minus PD of S, right? I'll take the LCM and I'll simplify this one. So what I'll be getting? 1 plus S2PS into 1 plus S2T into RS plus KPS into KT into S plus R into KI, isn't it? In the bottom, I do have this one. In the top, I'll be getting KPS into 1 plus S2T. 1 minute, sorry. I think there was a mistake here. I think I missed the term here, right? What was the term? Speed governor term, I think I missed. Right. So there will be a speed governor term also here. Yeah. This is my overall transfer function, and the steady state value I'm going to determine here. See, if you see limit s tends to 0, what I'm going to get? S gets cancelled. S into minus kps into 1 plus S2T, 1 plus S2SG into R into delta PD by, what is this one? 1 plus S2SG, 1 plus S2T, 1 plus S2PS into RS plus KPS, KT into RKI into KSG. Yeah, KSG is missing. Speed governor, I think I have forgot in the last step. So this is our. So if I substitute S tends to 0, what I'll be getting to here? Here, this one will become 1. This is 1. This is 1. This is 0, right? Anything into 0 is, this is 0. Here, what I'll be getting? KPS into KT into KSG. This one will become 0, right? So 0 plus anything, this is going to be my value. So this is one thing. In the top, if you can carefully see, this is 1, this is 1. This is R into delta P. So I'm going to partially implement this one. I'm going to partially implement this one. See here, I'm implementing, I'm going to get 1, 1, 1 into 0. So this will become 0 completely. So I'm eliminating this. So see here, minus KPS into, what is this one, guys? 1 into R into delta PD. But this is 0 plus. Yeah. But still, if you can observe, there is an S value here. So if I apply S here now, what will this become? This will become completely 0, which means the steady state value is finally going to be 0. Why? Because I have employed a KI. Since I have employed a KI here, integral controller, my steady state value has become 0, isn't it? We have done in the last class. We have got a steady state value in the last class, isn't it? What was the steady state value? It was 1 by 1 by R, like it was of some value. Now, let's check whether this can be achieved. This can be realized in MATLAB. Okay. So now I'm gonna show you the same thing in MATLAB. So what I'm gonna show, if there is any change in demand, this can be countered by the change in speed change setting. But since nobody wants any manual control every time, this can be set automatically by employing an integral controller in the place of manual speed changer setting. Okay. So if I integrate an integral controller into the system, then automatically my steady state value will become 0. The same I'll be now showing to you in MATLAB. We have developed already the complete block diagram of single area system in our last before session. And now we will take that model of a single area system and we will try to counter any changes in demand. And next we will also try to implement an integral controller into the system. Okay. Now, let me start the MATLAB now. 1 minute.
Welcome back to the simulation, guys. I hope you are able to see this one. This is the model which we have studied in the last class. I'm gonna do this one for you. So these two are the two inputs. One is a manual power changer, manual speed changer setting. This is the demand, electric demand. This is the speed kernel representation. This is the turbine representation. This is the generator load model. Now, for the case A, I'm gonna take that there is no control from the speed changer setting. So I'm keeping it as 0. And the demand, I feel that there is a 10% change. So I'm taking it as 0.1 per unit. And I'm going to run the simulation for 200 seconds. Now let's see how the frequency is going to vary in this one. So if you can carefully see that the manual setting is not in control. Only the demand is varying at 10% with 0.1 per unit. Now, what must happen to the system? Since there is an increase in the demand, the frequency must drop. Now let's look back at the frequency. So if you carefully see, the top one is the demand, it is 10%, 0.1. The second one is the manual power setting, it is 0. And see the third one, this is the frequency, change in frequency. Isn't it? I think it is very small. So I'll reduce my simulation to 80 seconds or so. Okay. And this particular signal, I'll clearly mention it as S. and this is PD of S. Now you can see it now. It is at 0.1. This is 0. This one, if you carefully see, it is finally settling down at 30% change in the frequency, if you carefully observe. Isn't it? This is why the frequency is varying. It is going down to 50% change initially, finally settling down to 30%. Why this is happening? Because there is a change in demand of 10%, isn't it? Now the manual power command has not changed here. So now this change in frequency, which is 30% at the steady state, let us suppose it is not acceptable for me. Okay, so what I should do, I should manually increase the generation to meet the demand. So how to increase the generation? I can vary the power changer setting. So now let's see if I can change the power changer setting. See, I'm gonna increase it to 0.1. So for 10% increase in the load, I'm gonna increase approximately 10% increase in the generation by varying the speed changer setting. See now, let's look back at see, the steady state value is 0. Why? Because the demand, which has increased by 10%, now is countered by the speed changer setting. See, this is also at 0.1. So that's why your steady state value is 0. Maybe because initially there was an transient, but finally my steady state value is going to be 0. This has happened because of my manual setting. So it is not really possible for me to manually control it all the time. So what I'm going to do, I'm going to implement a controller for you. So I'm removing this control. Okay, I'm going to remove this one, and in that place I'm going to implement a inverter function with a gain of, let us suppose, 0.09. I'm going to take, and this is 1 minute. These guys are making a lot of noise here. So this is the integrator. I'm going to fed it back, but with a negative symbol. Okay. Now let's see if I'm going to get the same result or not. Yes, I'm going to get the same result. If you carefully see, this is my same result in the steady change in frequency. See, the steady state value is again 0, isn't it? Now we will do one thing. We will take these 3 signals separately, and we will try to see exactly in one block what happens when there is a change in demand, when it is countered by manual power setting, and otherwise it is countered by a PI controller. Okay, so now I'm going to take this one as I'll do one thing. I'll take a subsystem. Yeah. Yeah. I'm going to take a subsystem. I'm going to place entire this thing into 1 minute. Yeah. I'm going to place it here. Okay. The first one, I'm going to take demand alone. This is demand alone. Okay. The second one, I'm going to take it as 1 minute. Second one is demand is countered by speed changer setting. The third one is demand is countered by PI controller. Okay, I'm going to make necessary changes in this one. This is the first one, this is the second one, this is the third one. First, let's see I'm going to remove this controller because what I need is this is PC of S, and this value is going to be 0. Only there was a demand, and this is the demand PD of S, okay? And the signal is going to be PC of S, okay? So initially it was only this one, okay? And the feedback was positive. This was initial one, and the second one is again this is going to be, yeah, so here in this one, if you see, there is a demand, and this is countered by my manual power changer setting 0.1 with 0.1. This is not true in all the cases basically, okay? And this one is my PI controller, which I have employed in the recent past, okay? Now let's see what the outputs of all these things are going to be. So for this one, I'm gonna take all the three inputs. I'm gonna sketch in a single graph, okay? The first one is going to be demand alone. The second one is going to be countered by speed changer setting. The third one is going to be countered by my PI controller. Let's look back at the system now. Uh, yeah, it is ready. Okay. Uh, yeah. You carefully see. The bottom one is the yellow one, is the initial one, which is generally, okay, for your sake, I'll make it as 3. See, the top one is without any countering. It was just only demand. Because of the demand, there was a change in frequency. The second case is countered by manual power setting. The third case is countered by my integral controller. See, if you can see, integral controller is also giving a steady state value of 0. But there are a few drawbacks of this one. One of the biggest drawback of this one is yeah. One of the biggest drawbacks is, see, the transient is nearly 50%. Go with manual control, it is just only 30%. So this is the biggest drawback of 0. The initial transients will be a little bit larger. This is what we call it as a peak value, and this is a settling time. Both are a little bit higher. Settling time, peak time will be higher, but my settling steady state error is 0. If you are more bothered about having your 0 steady state error, it's better to go with an automatic PI controller. Okay. So what is the conclusion for today? PI controllers can reduce the steady state error. Okay, thank you. Can reduce the steady state error to 0. So instead of going for a manual control, we can simply go with an PI controller. Okay. That's it for today, guys. Thank you. Thank you for joining. We'll meet in the next session with the 2 area system. Okay.